Hi and welcome to this tutorial on balancing equations. In the previous tutorial, we learned how to calculate molecular formula and empirical formula, or molecular formula from the empirical formula and the relative molecular masses, and also from composition by mass by percentage and general data and volumes as well. So in this tutorial, we're looking at balancing equations and Ionic equations too. So there are two things that you need to know about with balancing equations: conservation law and, of course, how to do a balanced equation. So having a good understanding of what we mean by conservation law. So matter can't be created nor destroyed. So if I've got 5 hydrogen atoms on the left-hand side, I must have 5 on the right-hand side. We do not have hydrogen atoms disappearing or appearing from nowhere. So that's our conservation. So that's especially obviously for a closed system. So it's called the law of conservation of mass. So in a closed system, the mass of a system must remain constant over time and cannot change, because we cannot have things magically disappearing into thin air. Substances cannot be added or removed from the system, of course, for that law to work. So it's when it's a closed system. And with a balanced equation, the number of atoms of each element is the same in both the reactants and the products. And I'm sure you know this from your previous chemistry knowledge. And balanced equations need to satisfy the law of conservation of charge and of mass. The number of atoms on either side of the equation in terms of balancing can only be changed by changing the coefficient, which is the big number in front of each compound. So to change the coefficient number of the atom, we are not changing the smaller numbers. And I'll make that a little bit clearer later on, because then you change the compound completely. So you'll see in these images, we are changing the coefficients, these larger numbers in front. So you can see some key rules that we use. So of course, the number of atoms needs to be the same on both sides, and some equations that's easier to do than others. Work element by element, so don't try and juggle too many things at once, and pick any element of a molecule first, but do try to avoid sole elements like hydrogen and elemental molecular oxygen. Leave those till last, because they can mop up the last few atoms remaining. And the net charge also needs to be equal if we're dealing with ions. And in the process, you might find yourself unbalancing a particular element. That's okay, don't worry about it. Just focus on the element you're balancing at the time and move back onto that element later on. And you will get there eventually. So sometimes it requires a little bit of patience and trial and error. And the more practice you do, the quicker you will get at doing this ultimately. Practice really does make perfect with balancing equations. You'll notice tips and tricks that you can use. So here we've got a question. It's a combustion question, and there are some pretty quick tricks we can use for this to speed you up in terms of balancing. But pause the video, give it a go yourself. First of all, I'm going to write down what I've got. So I've got carbon, hydrogen and oxygen involved in this, and nothing else. I'm sure from GCSE you'll have lots of different methods of doing this. This is going to be more thorough than perhaps I would do it, because I've been doing this for a long time, so I don't need to be writing as many notes on each side, but I am going to go sort of full out on this. So if we're looking at the left-hand side for each of these, I can see that I've got 3 carbons, I've got 8 hydrogens, and I've got 2 oxygens, because it's O2. And on the right-hand side, I have got 1 carbon at the moment, 2 hydrogens, and I've got 3 oxygens. So with this, I'm going to leave oxygen till last because it's by itself on one side. So I'm going to focus on the carbons and the hydrogens, because the good thing is carbon is only in 1 compound on this side and 1 compound on the other. So that makes balancing very, very quick for us. So if we choose to balance carbon first, we can see if we're balancing D, because you can see we've got different letters here to help me signify what I'm talking about. So if I'm talking about D, so what is that coefficient in front of CO2? Then it has to be 3, because this is C3 over here. Therefore, D at the moment has to be 3. So that makes life a little bit easy for us. And then we can readdress what our amounts are here. I'm not going to rewrite everything out, but if we do that, it means we have now balanced this here. Okay, so that row, my carbons, are equal. Then, why don't we have a look at my hydrogens? So if I have a look at C, so that is this one here, this hydrogen. Now I can see that I've got 8, C3H8. Hydrogen is only in one compound on the right-hand side, so therefore I've got 8 hydrogens on the left. I need to have 4 on the right-hand side, so it needs to be 4 H2O. So that's nice and easy. C must be 4. So let's readdress our balance. That means we have now balanced. That means I've got 8 hydrogens on that side. So that is balanced, and we've sorted that one out. Then I need to have a look finally at my oxygens. So at the moment, what I also need to do though is that these numbers will have changed because I've put different stoichiometric numbers in front. So let's readdress these and count how many we've got. So on the left-hand side, I've actually still got 2. I've got 2 oxygens. There are my 2 oxygens. That hasn't changed. And why don't I write out what we've got so far? So we've got C3H8 plus O2. That gives us 4 H2O plus 3 CO2. That's what we've got so far. So I can see that I've got 2 oxygens on this side. I've got a lot more on the right-hand side. I have got 4 oxygens here, and I've got 6 oxygens accounted for here. So I've got 10 oxygens on the right-hand side. So what can I do to balance that out? I need to get this number 2 up to 10. So I'm going to times it by 5. So if I put a 5 in front of there, that means B must be 5. And so actually, when I'm looking at this, this is balanced. So let's not forget, they've also asked me for A. Now A hasn't changed, but I still need to give a value for A. A is 1. We just have 1 C3H8. So that's an exam technique thing there. It would be common for students just to give D, C, and B and forget, oh, you do need to give a value for A as well. Here's another question to have a go at, so pause the video and give it a go. First thing I'm going to do is to rewrite that equation because it's going over a change of line, which is making it slightly difficult for me to interpret it. So B, PbO, C, PbNO3, 2, and D, Na2O. Okay, and I might go over some of these with maybe a different colour just to make that easier for me to see. Great, so let's write out what I've got. I've got sodium, I've got nitrogen, I've got oxygen, and I've got lead. So those are my compounds that I'm going to be using here. And on the left-hand side and then right-hand side, let's see what we have of each. So I've got 1 sodium on the left, 2 on the right, 1 nitrogen on the left, 2 on the right, 3 oxygens on the left, and 7 on the right, and then 1 lead on both sides. So we can fix both the sodium and nitrogen if A equals 2. So that's going to get us somewhere really, really quickly. So if A equals 2, so if I rub that out and put a 2 there, then that means we've now got a 2 and we've now got a 2. Now that's fantastic. That's those 2 lines fixed at the moment. Now, of course, that's going to change the oxygens. So I just need to consider that. I have put another, I've now made that up to 7. So that happens to have also balanced the oxygens. So look, I've balanced everything. Hang on a minute. I've balanced the whole lot super, super quickly. So if you just 1 movement, the whole lot is balanced. So A was 2, B is going to just be 1, C is also 1, and D is also 1. You can see my equation is balanced above, and all of these others don't need any numbers in front in order to balance. You can see how, even using that method, we can very, very quickly get to the correct answer. In case you hadn't noticed, there's no need to write a 1 in front of a compound where there is just one of it in terms of the molar ratio. It's assumed. So no need to do it. You can see here I don't put 1 Cl2. In fact, that would be really, really frowned upon, a little bit confusing. Okay, so just leave it blank. Only put coefficients in front when they are not 1. Here's another practice question. Pause the video and give it a go. So I'm going to write out what I've got. So I've got hydrogen, sulfur, oxygen, and boron. And I've got my left-hand side and I've got my right-hand side. So my hydrogen, I've got 5 on the left, 2 on the right. Sulfur, I've got 1 and 3, 7 and 13, 1 and 2. So we can balance the boron easily if B over here is equal to 2. So if B is equal to 2, and we end up putting a 2 in front here, then my boron is going to be 2. Okay, so boron's balanced, but of course that's going to have a knock-on effect. So we're going to end up with my oxygen here now increasing up to 10. And it might affect some other aspects. Yes, so it's going to make my hydrogens also increase up to 8. So I'm just keeping track of where I am with this. So let's balance our sulfurs. So we can balance our sulfur if we make A equal to 3. So if A is equal to 3, so I get rid of that and put a 3 in front of there, then that's going to start to change a few things. So now I'm going to end up with 12 hydrogens, and nothing's going to change the right-hand side. My sulfur is, of course, going to increase to 3. That's balanced my sulfurs, fantastic. But my oxygen is also going to change, and that's going to have changed to 18. So there's still a bit of work to do. So I've got my sulfur and my boron balanced. Now remember, as I go along, I might end up unbalancing certain elements, and that's fine. So then I'm going to look at the water first. And so now I'm thinking with the hydrogen, I've got 12 on the left-hand side and I've got 2 on the right-hand side. If I put a 6 in front of the D, so let's make D equal to 6. Okay, so if I get rid of that and put a 6 there, then let's change what we've got. So that is going to change my water, and that's going to make that 12. Fantastic. So that's now balanced. But of course, it's also going to have a knock-on impact on the oxygens naturally. And I'm going to have 6 more oxygens added in. But luckily, that is going to add 5 to this number. And that's going to make that balanced. So at the moment, by the looks of it, everything is balanced. So C is going to stay as 1. There we go, so C is equal to 1. So you can see eventually I'm just giving this, so it's going to be 3H2SO4 plus 2BOH3 plus B2SO4 3 plus 6H2O. And there is your answer. You might want to rewrite it as A, B, C, D. It doesn't really matter, but we got there. In terms of balancing ionic equations, we need to consider the ionic equation itself. So can you write out an ionic equation? Do you know what spectator ions are? And do you know your state symbols? Those are all really important rules for balancing them. So ionic equations are, of course, equations for reactions occurring between ions in a solution. So we've got an example down here of zinc metal reacting with aqueous copper, and we've got an ionic equation. Spectator ions, so they're ions that do not change state or charge in the reaction. So the ion is present in the reaction, but it doesn't actually react, hence it spectates, it watches. And so if we're having a look here, we can see some spectator ions. In fact, we can see lots. So we've got NO3, NO3, it's aqueous, on both sides, no change. And I've got sodium and sodium there, aqueous on both sides, they've not changed, they've not reacted. So those are our spectator ions. Whereas you can see that the lead is aqueous on the left-hand side and it's in a compound on the right-hand side. So something has happened there. It's not a spectator, it's actively involved in the reaction. State symbols are essential in Ionic equations. You have to include them. They cannot be missing. And they tell you whether something it features in the Ionic equation or not. So they're absolutely essential. So of course, you're either going to have a solid, a liquid, a gas, or aqueous. And it defines the state of the matter of the compound the molecule is found in. So here we've got some sort of back to key stage 3 examples of what happens with those. And you'll find that metals, they tend to be insoluble, and they'll nearly always be S, solid, when they're by themselves. So just Na is going to be S, solid. Acids found in the laboratory tend to be aqueous, so HCl would normally be aqueous. And certain elements such as oxygen, hydrogen, nitrogen are going to be gaseous at room temperature and pressure. And reactions in solutions are going to be aqueous as well. So here are your state symbols. I'm sure that you've come across them before. So have a go at this practice question. Pause the video, give it a go yourself. So in this reaction, we know that the metal is very likely to be solid, magnesium. So it's going to be in a solid state, then insoluble on their own. So if I dropped it in water, for example, it's not going to dissolve. The acid, like I said, H2SO4, laboratory acids, going to be aqueous, according to our rules. And then we've got a salt, MgSO4. So most salts are going to be soluble, like your table salt. So it's likely to be aqueous. And then hydrogen. Now hydrogen, we know it's a gas, the squeaky pop test. So it's a gas, you'll see effervescence or bubbling. So there we go, state symbols of each reactant and product. So if you're unsure about a salt like magnesium sulfate as to whether it's soluble or not, think about the metal plus acid reactions. So copper sulfate, as we've got here, is well known to be a blue aqueous solution. So this should help you realise that magnesium sulfate is also going to be aqueous. When we give ionic equations, we remove the spectator ions. We just get rid of them because they're not involved. They don't participate in the reaction, they just spectate. So an ionic equation usually only includes the particles in the reaction. So as I showed you earlier, I highlighted the spectator ions. So those are my nitrates and my sodium ions. So we're going to get rid of those because they're the same on both sides. They're in the same state. And so once we get rid of those, it just leaves us with our lead, our chloride ions, making our compound. And you can see there, I've just added those two together to make my compound and removed my spectator ions. And the products formed by reacting particles are also included in the ionic equation. Okay, so this is only if they're reacting in the solution. Of course, in an ionic equation, it's got to be balanced, and the charges need to be balanced as well. And the number of ions on both sides must be equal. So you might have to do a little bit of balancing equations in general, so the skills we were looking at before. Here is a summary of rules you can use for balancing ionic equations. So write out the complete ionic equation by splitting the compounds into their constituent ions. You need to have a strong understanding of polyatomic ions for this. Remove the spectator ions. Write out the net ionic equation that only includes the reacting particles. So if it's in the same state on both sides and looks exactly the same, then you get rid of them. If not, you include them. And check the equation is balanced and the charges are equal on both sides. So give it a go yourself. Here's a practice question. So here I'm going to write out, I'm going to split everything up into its constituent ions. So zinc is solid, so we're not going to do anything with that. Now copper, because it's aqueous, we are going to split those up. So Cu2 plus SO4 2 minus. So you need to have a good, strong understanding of polyatomic ions. Now both of those are aqueous, so I'm going to put aqueous there. And that's going to give me zinc 2 plus, which is of course aqueous, plus SO4 2 minus, because on this side, this is aqueous, zinc sulfate, so therefore we are going to split them up. When something is anything other than aqueous, we don't touch it, we leave it as it is. If it's aqueous, we break it, we split it up, plus Cu solid, so copper solid. Okay, then I'm going to remove my spectator ions. So looking at this image, I can see that the sulfate ion is on both sides, and that is the only spectator ion here. Everything else is going to be included. So I can just rewrite out my equation without the spectator ions, including the state symbols. And then I'm going to check it's balanced. Because I should have checked up here that it was balanced. Don't always assume that the examiner's given you a balanced equation, but it is. And there we go. I've got my charges are balanced. I've got a 2 plus on the left-hand side total and a 2 plus total on the right-hand side. And all of my state symbols are there, and there's no spectator ions. So that is my answer. If a substance does not have the state symbol AQ, aqueous, it means that it does not form an ion in the solution. So we leave it as it is. You'll see I broke apart my polyatomic ions apart, and just my ions in general. We don't do that. So an example is zinc, which is the state symbol solid, so therefore we leave it as it is. Remember, whenever you balance equations, you need to do a check at the end. So with normal equations, you just check to see if the number of atoms on both sides are equal. With ionic equations, you also need to check the overall ionic charge is equal on both sides.